Welcome to this comprehensive guide on dependency injection in Unity 3D, designed specifically for beginner game developers. In this video, we will explore how dependency injection can revolutionize your game development workflow, making your projects more robust and easier to manage from the ground up. Dependency injection, often abbreviated as DI, is a powerful software design pattern that significantly enhances the flexibility, maintainability, and testability of your game projects. It's a fundamental concept that, once mastered, will elevate the quality and scalability of your Unity games. It works by decoupling components, meaning instead of a class creating its own dependencies, these are provided from an external source. This external provision ensures that components are not tightly bound to their specific implementations, allowing for greater modularity and easier changes. This approach promotes modularity and reduces tight coupling, making your code easier to manage, test, and extend as your game grows. Imagine a system where changing one part doesn't break everything else. That's the power of reduced coupling. Let's explore the core concepts behind dependency injection. Understanding these foundational ideas is crucial before diving into practical implementation. First, dependencies are simply objects that a class needs to function correctly, ranging from other scripts and services to game assets. For instance, a player controller might depend on an iWeapon interface or a game data manager service to operate. Next, decoupling means reducing the direct connections between classes to minimize the impact of changes in one component on others. This allows you to modify or replace a component without having to rewrite large portions of your codebase. Then we have inversion of control, or IOC, a principle where the control of object creation and dependency management shifts from the class itself to an external entity. This external entity, often a container, takes on the responsibility of providing the necessary dependencies. A dependency injection container is a tool or framework that automates the creation and injection of these dependencies. It acts as a central registry, managing the life cycle and provision of various services and objects within your application. Finally, installers are used to configure this container, specifying which classes should be injected and how. They are essentially blueprints that tell the DI container how to construct and provide dependencies throughout your project. Now, let's look at the significant benefits of adopting dependency injection in your Unity projects. These advantages are why DI has become a cornerstone of modern software development, especially in complex game environments. DI greatly improves testability, allowing you to easily substitute real dependencies with mock objects for more targeted unit testing. This means you can test individual components in isolation, ensuring their correctness without needing the entire game to be functional. It also increases flexibility and adaptability, as dependencies can be swapped or replaced without modifying the classes that use them. This is incredibly useful for A/B testing different implementations or easily updating game features. You'll find better code reusability because decoupled components are much easier to integrate into different contexts. A well-designed, decoupled system allows you to take a component from one project and use it in another with minimal effort. Simplified code maintenance is another key advantage, as changes to dependencies have less impact across your code base. When components are loosely coupled, a change in one module is less likely to cause unexpected side effects in others, streamlining the debugging and update process. Finally, DI reduces overall complexity, allowing each system to be understood independently, accessing others only through intentional interfaces. This clear separation of concerns makes large projects much more manageable and easier for new team members to onboard. Now, let's dive into implementing dependency injection within Unity, focusing on Zinject and custom solutions. We'll explore both a popular framework and how you can build a lightweight system yourself. Zinject is a lightweight and flexible DI framework specifically designed for Unity, offering robust features for game development. It's widely adopted in the Unity community for its comprehensive capabilities and ease of integration. Its key features include automatic dependency resolution, modular code facilitation, and being component-oriented, tailoring to Unity structure. Zinject understands Unity's GameObject and monobehavior lifecycle, making it a natural fit for game projects. Zinject also uses installers for configuration, streamlines testability, and offers flexible injection methods like constructor injection. These features combine to provide a powerful and adaptable system for managing your game's architecture. Setting up Zinject begins with installation via the Unity Package Manager or its GitHub repository. This process is straightforward and typically involves importing the package into your Unity project. Next, create a scene context by right-clicking in the hierarchy and selecting Zinject-Scene Context. The scene context is a game object that acts as the entry point for Zinject's dependency resolution within a specific scene. Then, create installers by making a new C# script that inherits from monoinstaller and overriding the install bindings method. This install bindings method is where you'll define all your dependency mappings and configurations. Finally, link the installer to the scene context by dragging it from the hierarchy into the installer's property of the scene context game object. This step tells the scene context which installer to use for setting up dependencies in that particular scene. Zinject uses project context for dependencies that persist across scenes and scene context for scene-specific dependencies. Understanding the distinction between these two contexts is vital for managing global versus local dependencies effectively. Installers, as mentioned, specify how classes should be injected. They are the configuration layer where you bind interfaces to concrete implementations, define their scope, and set up any necessary factories or providers. Let's examine a Zinject code example for a player controller and iWeapon interface. This practical example will illustrate how Zinject simplifies dependency management in a common game scenario. Here, player controller depends on iWeapon, and Zinject injects an instance of player weapon through constructor injection. This means the player controller doesn't need to know how to create a weapon, it just receives one. The player installer binds the iWeapon interface to the player weapon class, defining this relationship. The as-single method ensures that only one instance of player weapon is created and reused throughout the application. Now, let's explore how to create a custom lightweight dependency injection system. This approach gives you full control and a deeper understanding of how DI works under the hood, without relying on external frameworks. The first step is to define custom attributes, such as inject and provide, to mark dependencies and their providers. These attributes act as metadata, guiding our custom injector on what to inject and where to find it. Next, implement an injector class that finds and satisfies these marked dependencies. This injector will be the central component responsible for scanning your code, identifying dependencies, and providing them to the requesting classes. Register dependencies by using the provide attribute to mark methods that will return specific types. These methods act as factories or providers, telling the injector how to create or obtain an instance of a particular dependency. Then, inject dependencies by using the inject attribute to mark fields or methods where dependencies should be placed. When the injector encounters an inject attribute, it will look up the corresponding dependency and assign it. Finally, use reflection to find all methods marked with provide and register them. Then find fields and methods marked with inject to resolve their dependencies. Reflection allows our injector to dynamically inspect and manipulate code at runtime, making the DI process automatic. There are several common injection methods. Constructor injection, where dependencies are passed through a class's constructor. This is often considered the cleanest method as it clearly states a class's required dependencies upon creation. Method injection, where dependencies are passed through specific methods. This is useful when a dependency is only needed for a particular operation or when the dependency might change during the object's lifetime. And property injection, where dependencies are injected through properties. This method is more flexible than constructor injection as it allows dependencies to be set after object creation, but it can also make it less obvious which dependencies are essential. Let's look at a custom DI example, starting with the injector class. This example will demonstrate the practical application of the concepts we've just discussed, showing how a custom DI system can be built from scratch. The injector class manages a dictionary of dependencies and uses awake to register and inject them. The awake method is a Unity lifecycle function, making it an ideal place to perform initial setup for our custom DI system. The register dependencies method iterates through components, finding methods marked with provide to populate the dependency dictionary. This method effectively builds a map of all available dependencies within your scene. The inject dependencies method then finds inject attributes on fields and methods across other monobehaviors and resolves them from the dictionary. This is where the actual injection happens, connecting the providers with the consumers. The iDependency provider interface and provide attribute are simple markers for our system. The interface helps us identify components that can provide dependencies, while the attribute marks the specific methods that act as providers. Similarly, the inject attribute marks where dependencies should be placed. This attribute is crucial for the injector to know which fields or methods require a dependency to be supplied. In this example, environment system provides itself as a dependency using the provide attribute. This means that any class needing an environment system can simply request it, and our custom injector will provide the existing instance. And class A injects the environment system using field injection marked with inject attribute. This demonstrates how class A can easily obtain a reference to the environment system without needing to create it itself or know its concrete implementation. Let's discuss some best practices for implementing dependency injection. Adhering to these guidelines will help you maximize the benefits of DI and avoid common pitfalls in your Unity projects. Prefer constructor or method injection over field or property injection for clearer dependency declaration. Constructor injection, in particular, makes it immediately obvious what a class needs to function correctly, improving code readability and maintainability. Always use interfaces to define dependencies. This promotes maximum decoupling. By depending on abstractions rather than concrete implementations, your code becomes far more flexible and easier to test and extend. Keep your dependency injection logic concentrated in the composition root layer of your application. This means centralizing the configuration and setup of your DI container, typically at the application startup, to maintain a clear separation of concerns. Start small and experiment with DI in areas where it can bring the most significant benefits to your project. You don't need to refactor your entire game at once. Begin with a few key modules to see the positive impact firsthand. While powerful, dependency injection does come with potential challenges. Being aware of these can help you navigate them effectively and ensure a smooth implementation process. DI can sometimes increase complexity if not implemented correctly, especially in larger projects. Over-engineering or misusing the pattern can lead to a convoluted setup that is harder to understand and maintain than the problem it was meant to solve. Reflection, often used in custom DI systems, can introduce a minor performance overhead, though it's usually negligible for most game applications. For performance-critical sections, it's wise to profile and ensure reflection isn't causing bottlenecks. The initial setup of dependencies can also be challenging for newcomers. There's a learning curve involved in understanding how to configure containers and define bindings, but with practice, it becomes much more intuitive. By understanding these core concepts, benefits, and implementation methods, you can write cleaner, more maintainable, and testable code in Unity 3D. Dependency injection is a skill that will significantly enhance your capabilities as a game developer. Whether you choose a framework like Zinject or create a custom system, dependency injection will significantly improve your game project's architecture and scalability. It empowers you to build more robust and adaptable games that can evolve with your vision. Thank you for watching this comprehensive guide on dependency injection in Unity 3D. We hope this video has provided you with valuable insights and practical knowledge to apply in your game development journey. Happy coding!